Welcome everyone for this new MLIR meeting. And today Scott is going to talk about some work he's been doing to allow data visualization across IR transformation. Scott.
Awesome. Morning or happy time zone, everyone. I'll put a link to the slides in the chat as well. They're also linked on the discourse announcement, and they'll be available afterwards too. There are a bunch of links in there if you want to follow along or dive into some more details. Yeah. So I wanted to talk about both a little prototype that I've been working on for some data visualization. Then after a brief introduction to the new tool, talk about why I set out to build it at all and what other things are available. Then circle back around and go a bit deeper on the details on how this is particularly useful directly for the Erie project, but could also be useful for others. And then I have some questions around how to implement this so that it's more broadly useful and how other people could take advantage of it. Regarding questions throughout, probably during these two sections would be best. I like to put the little introduction at the start to give people a taste, and then we can go and get into the nitty-gritty. So this is what I made. It's a chart driven by some JSON data. This particular data is from Erie compiling a simple function that just computes the absolute value of a floating point number. And it shows kind of, you can think of it as if you do a print IR after all for a run of a compiler tool, you get the IR after all those passes kind of in a big text file. If you take that text file and kind of flip it on its side, you get a graph somewhat like this, where the pass number is the x-axis. So we start from the input IR and we end at the kind of final output from the tool. And the y-axis is the number of ops in the top level module throughout that compilation. So as compilation proceeds, we go from our little simple input IR to something more complex. And each series in this stacked bar chart is colored based on which dialect that particular count of ops is. So for this example, we can see this big blue swath here is Erie's HAL dialect, our hardware abstraction layer. So that kind of comes in early, persists for a while, and then drops out entirely as we switch to our virtual machine VM dialect towards the end. And you can see some other bits in here around the lighter blue, the LLVM dialect as we do our code gen in the middle, and other details for the other various dialects. So kind of useful as a tool for seeing where dialects enter and leave and how the different passes work with those dialects through the multi-level compilation. And it's interactive, so if you're following along with the link, you can click, you can drag to zoom into regions, you can mouse over and see what pass each data point is and the specific count at that point. So that's the tool I've made. Stepping back a bit, what else exists and why did I think this would be a useful addition? At a basic level, a lot of work involves looking at IR and printing IR in various different ways and kind of looking at it. It's kind of the raw data that you're used to working with for an individual pass or even for a larger pass. And there are all these different tools. You can read the docs to see all the different variations of ways that you can print. So you can omit particular prints if nothing actually changed there, or if you have large constants, you can elide those. You don't have a gigabyte file, you only have a few megabytes in a file. You can choose to print after specific passes, all sorts of ways to slice this. But this is still, when you get into very large models or lots of passes, it can be difficult to spot patterns in this kind of output. Also, as an aside, you can do pretty things like convert your plain text into a markdown file and use syntax highlighting. This is a GitHub gist using the MLIR syntax highlighting mode for an IR output. We have a little script that I just added that does that conversion for you if you want to publish snippets of IR from those dumps on GitHub gists and just have section by section views into that. And another thing we found that's particularly useful
Just Scott, something you didn't mention in the visualization that exists in Tree is the CraftFace visualization that allows to see as a graph the data flow graph of SSL value, I think.
Yes. Yeah, I haven't tried that out myself in a while, but definitely very useful, particularly when you're doing that kind of graph analysis and you want that view where things can branch out and then fold back in.
I saw some patches on this recently, so I know it's active in development in this area.
Awesome. Tracing is another tool that we've used a lot in Erie for measuring performance and digging deeply into performance. On the left here, we have a instrumented view of running the compiler through Erie. So each of these tiny ops, this is normally a desktop tool that you zoom in and zoom out and get all these different views through. You can see the size of each block is how much time was actually spent. So the time scale here is on 20 seconds for this whole block. We have fairly serial execution, and then at some point we branch out onto multiple threads and run passes on individual functions and then fold those back in at the end. And if you run it in a sampling mode, then you don't need to actually edit your code, but you can still get a breakdown of where time is going based on the samplings from that profiler tool. You get source locations, and you can dig through and try to sift through the massive call stack to find where the things are that you care about. Yeah, happy to go into details, and I'm sure Ben is as well if anyone's curious on how to set up this kind of profiler and get information out of it.
Yeah, I guess one interesting thing to point out here is this is how we, at some point, we had several minutes of compile time, and with just a couple days of going through this, we got it back down to under 10 seconds or so. So useful if you find yourself in a situation where somehow a n-cubed algorithm snuck into a big IR tree and you need to kind of figure out what's going on. In particular, we've seen things with symbol table lookups that were uncached, and so like a canonicalization pass got a symbol lookup in it that was then running 100,000 times per pass and stuff. So really useful if you find yourself with long compile times. This is a good way to dig into that.
There's a question: what parallel code is this? CUDA, OpenMP, MPI. So this particular data here and most of the other data that I'm working with is particular to Erie. So we have our compilation pass. To skip ahead to this part a bit.
I think that was specifically about what is doing the parallelism here, and this is the LLVM parallelism during compilation.
Yes, yeah, and Erie itself targets through LLVM on the CPU and Vulkan for the GPU and CUDA for parallelism. So getting back to this, have a labeled version of that chart, which you can kind of analyze on your own if you kind of poke through and see interesting spots. But it also helps to have some system knowledge as well. You can see the various phases in Erie's compilation through the 200 or so passes here, where we kind of start with some legalization of the input, do some common transformations there to simplify the IR, convert to forms that we work on generically down the line. Then we kind of enter our hardware abstraction layer, dialect, and get ready to do our LLVM code gen. So we start splitting apart the input module into different pieces that we'll throw at CodeGen. Then we have our CodeGen pipeline operating on the LLVM dialect. Notice that there's a bit of memref in there, and there's kind of a bit of standard dialect throughout. The Erie dialect is kind of our utility dialect at this point. There isn't too much in there, things that we find useful in our compilation. Then LVM disappears here, so that's where we throw it off to not the LVM dialect, but LVM itself to go and take that IR and compile it down to machine code and then serialize it into a blob of data that we can carry on through the rest of our program. We do a bit of cleanup there. And that this is kind of another insight of this type of tool. Do we actually need this cleanup? It doesn't seem to be doing much to the IR. So that could be something that we can follow up on and see, what are these passes? Are they needed? Are they checking for code motion in loops or canonicalizing or other things that have already been checked before? And this was just in case things that 2 years into project development later don't actually matter anymore. They may have mattered at one point. And then we convert all of this into our virtual machine dialect and get that finalized. And if we were to, say, go from here to emit C and generate C code, then you could see another section at the end here where this goes to the emit C dialect. If we were targeting Vulkan and the GPU, you'd get a similar graph, but instead of having LLVM here, we'd have SPIR-V. And then a somewhat similar set of passes with the rest of the compilation all similar. This is a more complex example because this example was just an absolute value of a single number. This is kind of a real model showing some more complex behavior. And you can see the difference in scale here. Now we have over 1,000 passes and 40,000-ish ops at the peak. But that actually we're normally dealing with 5,000 or 15,000 ops outside of this particular point in the graph. The CodeGen is a longer buildup. This part is actually where it fans out and runs these in parallel because these are separable sections. But the way that this visualization is developed, it flattens it all by disabling threading. And we can notice some things about this kind of graph where there are interesting points where canonicalize is really simplifying the IR, or where exploding the number of ops and then shrinking it back down. And if we didn't have this deduplication pass happening here, maybe this whole part of the graph would be massive. We can see more patterns. Like here, the affine dialect existed for a bit, and then it all gets converted to standard. So the standard dialect, the pink here, kind of takes up whatever was in affine. You can see the motion through the colors there. And yes, we have 15 dialects across all of the compilation here, and not all of them exist at all times. Sometimes we have 8 or 10, or at the end just 1. But it really gives you a sense for what that distribution is over time and how each part of the pipeline uses the various dialects. Any questions at this point on either our particular compilation flow or the way the visualization is set up?
Someone just had a question in the chat about what exactly pass number meant, if you wanted to explain that again.
Oh, yeah. So this is running using a PassInstrumentation, and that gets a callback from the pass manager whenever a pass is executed. And it's just dumping those kind of in serial with threading disabled to a JSON file. So if you did a print IR after all, the time that that pass ran would be what this number would be. If you split out and say add nested pass on all functions, then you would get one pass number for each of those runs on where it runs on each function. If you had a pass that operates on the entire module, that would appear as one pass.
So are you using a single pass to run thousands of times, or are you using thousands of passes?
Each particular pass runs a different number.
Oh, okay.
Yeah,
Okay.
what the pass number here can be the same pass repeated over and over.
Oh,
Yeah,
okay.
so-
Okay, I see.
Or it can be multiple paths. You don't know on this graph because
Okay.
it's really printing the IR after the application of a pass, independently of if it's the same over. And that's what Scott was trying to say. If you have a module with 1,000 function and you
Mhm.
run the canonicalizer on each function individually, it will show up with one little bar on each
Mhm.
individual function. Because
Oh, okay.
that's the granularity of the pass manager.
Okay, okay. I see. Thank you.
Which is why we have far more passes for this bigger model
Yeah.
than we did
Okay.
for absolute value.
Mhm.
Yeah, so it just shows you the evolution of the code as it is transformed, independently of the pipeline, like the pass pipeline you define to some extent.
Okay.
There's not a direct correlation, and so I think for example the boxes, Scott, you showed before when you were saying like the various phases of your pipeline, they were like added by drawing on the graph. But those boxes are interesting. But maybe what would be interesting is like, could we give a notation that would allow to recorrelate those data to the passes or the phases of the tool?
Okay. Thank you.
You have another question, Scott?
Yes. The question is, are the visualizations a list of specific UIs, or is there an interface to customize what is displayed? So what's built right now, and I'll kind of reference the code. It generates some JSON that's kind of generic data, and then there's one specific HTML JavaScript visualization of that data. And if you wanted to, you could go in and edit that visualization and slice the data different ways, or choose other ways to display it. Also, is it possible to display, analyze runtime metrics, time, compiled size, heap usage? Yes, though this visualization may not be the best fit for that. One thing that might be useful would be on these tooltips to put time to execute that pass, or some other little bits of metadata. When you're trying to measure time that the compiler takes, or time that your runtime takes, or the memory usage, it helps to go to a profiler for that, like Tracy, where you can actually get the time run for a particular piece of code that gets instrumented. Tracy also has memory metrics and all sorts of really cool advanced features for digging through that. Yeah, so talking of I wonder if there is value in treating the passes as a DAG and looking at critical path and average parallelism. Yes, this particular visualization makes the decision to flatten out of the graph into a linear view for viewing these types of patterns. If you're more interested in the flow through the graph, or how much your fan out is at particular points, then yes, you could totally load it into some sort of graph view, or generate some other metrics sliced that way. For the particular implementation of this one, the the C++ code to generate the data is pretty much just this, and then a bit of glue. It's a pass instrumentation that gets a callback for every time a pass runs, gets the pass and the operation that it ran on, and it goes through and counts the number of times each dialect appears, and then writes that into some JSON. And you get a JSON file like this that has, this is the pass name as just the string that you get in C++, has an array with the HAL dialect had 2 ops, the standard dialect had 4 ops after this pass, and then it moves on to the next pass and add some more JSON there. So there's plenty of space here to add other metadata or other summary statistics, or do things like count before the pass and after the pass. Then on the visualization side, it's just 200 lines split between a few web dev files. Basically loads the data in, does a bit of processing on it to get it into a graph-friendly format, and then was it a charting library. I just picked Canvas.js because it was convenient, and set some styling on it. So series 1 is this color, series 2 is this color, the x-axis has these labels, those types of things. And then the charting library does all the interactive stuff and summarization for you. Yeah, so I had some questions about the implementation of this, and was also curious to hear if other people would find this particularly interesting, or similar ideas interesting in getting them upstream in some format, or finding ways to adapt them for their own projects. The main thing that I'm a little hung up on is how pass instrumentation runs on a particular instance of a pass manager. And in projects like Erie, we happen to have 3 of these. They don't all have equal amounts of code, and it's interesting enough to get the one main one, but it would be nice if we could get this type of output merged from all of them. And in Erie's case, we even have 2 separate binaries that run. We have an import tool and then our main compiler tool, and they're both using MLIR, and it'd be nice to get the data from them together. But the way that pass instrumentation is set up, you don't get enough metadata from it right now that I could find that would allow you to do that correlation to know this chunk of data appears before this chunk of data, or maybe interleaved with this other chunk of data in this time series way, especially across tools. And one idea that I had for that would be to add some sort of pass number or counter or timestamp or other metadata. So when you get that callback, you know this run after pass is for pass number 50. And then the next time it runs, you get 51. And then you write those to your file. And then you have a separate file. And if one of the files is missing 50 through 60, and the other one has them, then you know that you can put them together that way. Another thing that I'd really like to be able to do would be easily go from the visualization to the IR output to know, like, when those canonicalizes were doing a lot of work, what was the actual IR? I'm curious if it needed to be doing that much work, or what, just for my own education, what are we doing that canonicalizes away 2,000 ops? That's interesting. But the way that this is set up right now, I have a JSON file that has canonicalize as the only way to identify it. And one of the canonicalizes towards the end, and then I have my IR dump that has 50 canonicalizes in a row. I don't have a good way to map between that. If I had an ID to say the canonicalize that ran on pass 2030, then I can map between that pretty quickly and go back and forth.
I wonder if it's if it could connect to, like, River worked on debug actions, on which we were planning to build a concept of fuel, compiler fuel, and this kind of thing that allows you to stop after a given number of action taken by the compiler. So I wonder if this could be used to provide what you need. I'm not saying it's ready for free, but the foundation may be there. I don't know if River is online. Yeah, River is online. Do you have any input on that?
I completely missed what you just said.
So Scott was looking for ways to keep a monotonically increasing number that would uniquely identify the application of a pass. And that, to me, resonated with the work on debug action and compiler fuel for bisections of pass application.
Yeah, I think debug actions would be the only reasonable way to get anything monotonic in across pass managers, at least. Because, I mean, we don't want to have any shared state intrinsically between them. So it would be kind of something that you write and inject on your own using debug actions as the external hook point. Which I guess could be interesting anyways for debug counters, having a debug action for pass execution in there.
Right.
Yeah, I tried some really hacky things to store program static state and try to merge the JSON as it was being created, and that just didn't go the way I wanted it to. Having some standard way to get the monotonically increasing counter for joining these would probably work out much better, and then either within the program itself doing the merge before writing out to files, or having an external tool that says, oh, if you give me 2 of these, I will splice them together as best I can. Or you could throw a zip file at the website and have it do that on its own. The other kind of nice to have thing that I was reaching for would be having some other metadata available to either the instrumentation, if it could go up in the C++ hierarchy from pass or operation somehow and get some other metadata, or if you pass metadata into its constructor, then it could write stuff like the version number of the compiler tool, or the git commit hash for a source build, or the input flags used, or the source location for when a particular pass was added to the pass manager. Then this metadata could get written to the file, and then you would have, instead of just a loose JSON file that doesn't really tell you much other than passes had ops in it, would actually describe itself in some way to say, I was run at this version on this data using these options, and here's what I found. Then you could look at one of these afterwards and get enough information about it to better understand it. And some other questions that I had were around contributing. So I think the instrumentation itself in the C++ is pretty straightforward to add or wire up, and then people could expand on this type of data generation or write their own in a similar way. But I'm less sure about the kind of dev visualization. If there's like a utils area that these things could go in, or if they could live out of the project. It's not strictly necessary to have some way to handle the data, but it's nice. And integrating into some sort of easily available extension would also be cool, though I don't quite think the run this tool on your big pipeline fits into the
Is it
extent.
static in the sense that serving those pages can be done directly locally? Do you need a website? There's no server-side scripting, right?
Yeah, no server-side scripting.
Because
The
then
one I
if
have
it's
just
in-
pulls in some CSS and
if it's in
JavaScript from some
the
CDN.
if it's in the util directory, then that means you can run it locally directly. You just open locally in your browser the local HTML page, and you have everything at hand. So as a developer tool, in general, I like when it's just included in the util directory in the
Yep.
same place. I think we already have a Jupyter netbook things. We have those kind of things. The VS Code, Visual Studio Code.
It's also kind of nice if you we've done this before, where if we could host some version of it on the doc website, so you could actually if there was some way with URL parameters on there to create permalinks to it, because then you can email those around and everyone can see them without build steps and whatnot. There's a little bit more involved with that, some bits to put it on a gist and whatnot, but that'd be pretty slick for information sharing.
Yeah, if we can use GitHub as a way to store the JSONs, then we don't have to code a server ourselves. Yeah, that's a good point.
Yeah.
Yep. Yeah, we've done this for other tools where Stell said you put a query parameter, and then your JavaScript just needs to know how to fetch from that and get data from it. So GitHub gists or drive files or some file server, as long as it's visible to the domain running this, it can then load it in.
And as long as you've paid the requisite dues to the cross-site scripting gods.
Yes, exactly. Let's see. So there's another question in the chat. You probably discussed this, but tracking provenance, state, commit hash, compiler options in the JSON will help see how things have evolved over time. Something egregious happens with build times. This might help trace it. Yes. I love when tools are set up that way, so you can view the historical data and correlate across them. I usually find with this project and others that you wish you had that years ago to have the backfill data to get the really rich experience of looking at it over time. But starting today or whenever to generate that data and have the history of it pointed at Git commit hashes or some other metadata is still good.
You also mentioned in your last slide integration with the VS Code extension. So have you already looked into that? Do you have idea about?
I've thought about it. Conceptually, it's nice when the tools kind of grow in their feature set in ways that make sense given what they already have. I'm not really sure that this particular style of run a 5-minute compilation to generate a file and then have that visible in your editor is the most directly useful integration point for that. Having some sort of instrumentation generate data and then visualize it does seem like a natural extension, whether it's for this visualization or maybe for an individual pass. If there's some statistics that would be useful for, like, you look at your lit test file and you want to know a little bit more about what it's doing, that would be maybe a better fit for an extension. Oh yeah, another detail with the adding an identifier. I found when doing a print IR before all and a print IR after all, is that when you have nested passes, those can sometimes be disconnected in the IR because you have some stuff in between them. And what I would kind of like for this type of view would be a way to click on the tooltip and say, show me before and after this particular pass. And maybe there's some other stuff that happened in between that was nested. But if I'm curious about this, like this jump down here, what happened? Where did the LLVM dialect go there? What was that? What was that diff? Would help to know that the before IR after all and the after IR were the same particular pass.
Can you print the IR inside your JSON?
I could. It would get very big. It helps to have these files separate and some way to link between them. I have some of these on my file system, and the IR dumps.
Can you use a hash system then? Because in your instrumentation, you can have a directory where you print the IR that you can just hash the content and use this as a file name, and then you use this in the JSON to reference them.
Yeah, that would probably work. For some of these larger models, the IR dumps are hundreds of megabytes to tens of gigabytes, and they'll get bigger. The JSON is not too tiny when you get into thousands of passes, but it's much simpler.
Are you using the limit element adders big long flag that I can never remember?
Yes.
Yeah, it would also be nice if that flag, if we had a way to only apply that to the debug output, because it does mess up tooling flows sometimes that do that if they if they're actually operating on ASM.
Right. Right. You actually need the final output to pipe it to another tool, but you want the print after all to be elided. Right?
Yeah. Or and not just the print after alls, but like if you happen to be doing dash debug stuff and whatnot. And,
yeah. I think it's already kind of doable, but only in your tool, in the sense that when you print your final output that is semantically important, you can control the options you're passing directly and not pass the command line options to this.
Correct. It gets a little bit awkward. You know, in terms of like wanting to provide some debugging options to folks, but not, you know, needing to know what those are so you can then disable them, or you just disable all of them. And
Scott, do you want to talk about, and we discussed this in the team meeting the other day, so I'm not asking the question again because we already talked about it, but like the idea of instead of like different visualizations, we talked about like kind of flattening the DAG in different ways and combining passes and that sort of thing, which I think is maybe interesting and related to this like pass identifiers.
Yeah, so right now this type of graph just runs on the kind of raw every single pass without the omit passes that didn't actually change the IR or other options that the IR printing has. We could do something with this, like label which passes here didn't actually change the IR, and then you could get a visual view that if you, or that could even just be a raw statistic that you get from the passes. You don't need to go into an entire graph for that to see. Of the 2,000 passes, 200 of them didn't change the IR. You could then visually see which ones did that, and if they were clustered in some area, like maybe these ones in here that are just doing canonicalized loop coalescing, affine loop fusion, loop invariant code motion. It's probably running those 4 passes over and over again on a bunch of different functions here. Maybe in Erie at this point in compilation, those passes are outdated and don't need to be there. Like we could see the total number of ops here, the 4,921 is the same. So yes, they aren't actually changing the number of ops. Maybe the IR is changing a little bit within those, but I doubt it. and the flattened view here is running with disabled threading. We could also, as Mehdi pointed out, with some other tools, have those kind of graph views through the compilation.
Yeah, I think one thing that I would find interesting would be, rather than each pass getting a different number, if it's like serialized differently, like if the same func path on all functions was one bar in the chart, which we could do if we had pass identifiers. You could just combine them again. Because I feel like
maybe this whole big block here could get collapsed down a lot.
Because I think the way it does it when it does it serially is like if you're nesting into a function, it runs the full func pass line on that function, right, and then goes back to the next one, as opposed to like running the first pass on all functions, the second pass on all functions. But I think like conceptually, to me, that latter thing is what's actually happening. I mean, okay, that's not really relevant, but like in terms of the value of one pass, like it's what happens after it's been run on all functions.
Yeah, I wonder if there's some data that we could get from the pass here or the particular op, if there's something we could write in to say this pass originated from or is nested under this, to do some aggregation that way.
Yeah,
you should look at what the timing stuff does, because it does that exact thing.
Okay. Cool.
So it's like when you're timing a pass, it doesn't do, I mean, it aggregates for every function across threads. So it's kind of similar-ish in that way.
But does it work across Pass Manager, Joe? Because I think what Erie is doing is a bit weird there, in that it disconnect the. You have a pass that will instantiate a new Pass Manager, if I remember correctly, and that will call run on this nested Pass Manager. I'm not sure it connects the unclosing Pass Manager timing to the nested one.
I mean, yeah, I mean, that's not a supported use case anyways, so.
Well, we do, I think at this point we just use the nested passes.
The dynamic pass pipeline or something
I think that's how we're doing that. We used to have our own custom thingy because that didn't exist.
Exactly.
I'm pretty sure I successfully destroyed it all and used them. So hopefully that's a supported thing.
Yeah, that's probably connected then. Yeah, so look at the timing then. The timing infrastructure will show you some facilities to correlate those.
Okay.
That said, a mode in the compiler which would slice the pipeline so that it runs on like what Jeff was saying.
Yeah.
Run this function pass on all the functions before moving on, instead of run this set of function paths on this function before moving to the next function, can be an interesting visualization as well, especially for what you want to see here.
I think I would even like it for like a print-IR after all mode, because I find that happens a lot with print-IR after all, where I get totally lost because the functions are interleaved, but like actually running it in that order, I don't know how to describe that order, I think, and then printing it after the func path is run on all the functions, I think would be useful.
Yeah, it's we have a feature called that is coalescing the pass managers, meaning if you create a function pass manager and you add one function pass, and then you create another function pass manager and you add another function pass, in the end, what MLIR does is that it merges those two and says, oh, I'm going to take one function and run the two passes and then move to the next function. So what we want is the opposite, is a split of those pass manager, and so that we schedule them on all the functions individually. One function pass per pass manager.
We used to do that for the crash handling. So the code existed at one point, but not anymore.
Oh, we did? Okay.
Yeah, that's how it used to give local reproducers. It would split the pipelines so that effectively you would have one pass all the way down. But that doesn't really work for nested pipelines, really, because you have no control over what the user's going to do.
It seems like that would also enable you to have things like print-IR after all and still have some level of multi-threading, which would maybe be nice. I don't know. I guess when you're running print-IR after all, you usually don't care about speed, but like you could still be running all the func on all the functions in parallel and then come back together to print, and then like basically treat everything as a module pass. But like the fact that it's running on different functions is an implementation detail.
You can't actually do that because you could have multiple levels of parallelism down the tree. So it's not one parallel thing at a time. You could have a function pass running alongside a module, well, a function pipeline running inside a module pipeline, which they all get parallel via nested pass pipelines weirdness.
Sure. I'm not saying it works with like the normal threading. I'm saying you could have some amount of threading and it would be possible, but maybe it's not worth doing. But
Well,
yeah.
the problem was, how do you know that those passes themselves will not have deeper nested pipeline execution where you also want to print something?
Yeah.
I guess that's the problem that River was saying, is like, now you have those function paths, but each of those function paths will have a dynamic pipeline, right? Now you run on each function one after the other, but each of them will have its own pipeline, and you still want to print in those individual pipelines. It's complicated.
I don't know if you saw, Scott, but Mahesh has pointed out that while we're running affine loop fusion, we have no affine ops, which probably explains why that doesn't do anything. Maybe it would be good to check that we have any affine before running this affine thing.
Yeah, because I don't know if it's a structural property of the entire compiler or just for this particular model, but we run out of affine when we convert affine to standard around here.
Yeah, so if
No
you
more
convert
affine.
affine to standard and then you do affine loop fusion, that's
Yeah, it doesn't seem super useful.
I think that would be a good tool, actually, is change detection, or how often that a particular pass mutates something in your pipeline. Could be interesting to aggregate across all of your models that way. I don't know if this tool specifically could provide that in some form, but that seems useful as a thing. I mean, if only one of your models ever has affine loops at that point, then it's like, why am I running this?
Yep.
what can be interesting as well would be correlating things like, this pass didn't change the IR, but it still took time. And so correlate the usefulness of those passes maybe.
Yeah.
Yeah, I was looking at this particular section yesterday where we explode to 40,000 ops and then we deduplicate them over here. So I was wondering, can we deduplicate over here instead? Do we need to run these other passes? Like, are these canonicalizes really necessary? And kind of, maybe technically not. And
Well, you could also you do both. Like, you can try to deduplicate before running canonicalizer, and then run canonicalizer. Maybe you're going to find more opportunities to deduplicate after canonicalization.
Yep. Yeah, I timed this using Tracy, and this particular canonicalize that runs on the entire set took 2 seconds out of 20 seconds total. So if we move the deduplicate up there and then canonicalized after, we would save that 2 seconds. And
this is where
then it would be cheap to run again after canonicalize.
This is where pass timing helps. I know you said, I mean, if you're going to do deep diving, using a proper perf tool is obviously recommended, but the goal of pass timing and timing in the compiler in general is not to give you that. It's to give you like an indication from a high level of like, here's where you should focus your profiling efforts. So, I mean, if you had that here, like someone mentioned earlier, you could see immediately, or at least have an idea of like, okay, this section is taking this much time roughly. It's not completely accurate, but it lets me divert my time from a single view of this tool. Still useful.
Yep. Cool. Anyone else have other questions or would find this type of tool useful for your own projects? I'm curious to see what the visuals would look like for other projects, to see which dialects are they using, how many passes do they have, Are they more organized than us, less organized? This looks like kind of a mess, but it's a bit organized.
Do you have plans to extend it beyond just the op name or the dialect, I guess?
Um,
I'm trying to think of what would
like what?
actually be in tree. If it's just like JSON dumping the print op stats pass, or if there's intentions to add more things or that kind of stuff.
Yeah, I wasn't too sure about that, and would be curious to see if other people have similar things that they would like to do with the raw data. For now, I was just calling it data visualization pass, but there could be other data visualizations that would want other data, and there could be other things that you could use this data for. Because it seems reasonable to me to start from the concrete use that I have already with this particular schema of data and the one visualization using it, but it'd be nice to find other ways.
Well, I mean, it seems like a lot of other there's going to be a pretty large class of things that would get what they want just by adding more keys in here, and
Yep.
you know, it's topologically in the right order, and you know, having a way to have anyone be able to dump you know, an analyzable file would be kind of nice, and then we can shove more stuff in there.
Yep. Yeah, and I'll say it now, I'm not too concerned about the file size of this particular schema growing too large as data goes in there, but I could certainly imagine it getting unreasonable if people start putting the actual IR strings in there or some other large things.
I mean, I have seen this sort of thing abused for orders of magnitude more than you're shoving in here. I'm not that concerned about it.
Yeah.
For the next 5 years.
Yeah, and then it's just up to the particular visualization to extract what it wants from the JSON.
Yeah, I've looked at some of these visualizations that you know, when we like run them across a cluster or something, are like take a minute to render, and we're a long way from that.
Yep. Yeah, I was happy to see it handle the larger 40,000 across 2,000 or 1,500 without any real issues. Go to the website and just load a different one. Loads pretty quickly. This one has 2,000, and that was another thing that we weren't sure about looking at this. Like, does our reference CPU backend having twice as many passes make sense as the LVM CPU one? Maybe you can see all the particular passes that are involved there.
To be fair on that one, we're not seeing any of the LLVM passes that we're running on the LLVM stuff. So this is a difference between pure MLIR and only MLIR passes running versus a bunch of LLVM stuff running in a sandbox that we had away.
Yep.
I mean, as long as it's not hard-coded or envisioned just for this, I'm fine with adding it upstream. And then proper documentation for how to use it, et cetera, et cetera, et cetera. But it looks really good. Looks cool.
Awesome.
All right. Well, thank you, Scott, for the presentation, and thank you everyone for attending. And I think we can leave it there. See you maybe next week, everyone. I'm not sure I have a confirmed presentation for next week, but maybe we can have also just a discussion on some topic. We'll see. All right, take care. Bye, everyone.
Yeah.
Yep.